Good evening to you, dear members. Hope you're doing well. In the previous discussion, we had an example on simple transient circuits. Today, I have come with another example. Hope you understood very well the other example and you explained well to your fellow students. Right now, as you can see in the diagram, we are having a circuit as shown above. In the previous example, we talked about the basics or basic techniques of solving the transient circuits. Today, I have brought you another tactic or technique of how you can solve these circuits in a simplified way. In the circuit above, the switch opens at time t equals 0, and they're asking us to use Laplace transform to find out the output voltage at any time when time is greater than 0. Our first step, as in the previous discussion, is to analyze the circuit for storage devices. Remember, we said when you see a circuit with a storage device, a capacitor blocks DC, so it acts as an open circuit, and an inductor shorts the current, so it acts as a short circuit. Therefore, when the capacitor is replaced with an open circuit, we can see it clearly down there in our next diagram. So after redrawing the diagram and analyzing it fully, we can come to conclusion using other tactics. For example, here I used source transformation. As a student, you can also apply superposition and other tactics or techniques of solving transient circuits can also apply. In source transformation, let us see how source transformation is done. Let us see how we can apply source transformation on this diagram. Now, when you are transforming a circuit, for example, in this diagram, when you look at this side, we are having a current source, we are having a resistor. If I want to transform this current source, this circuit, into a voltage source, what I do, I have a current source in parallel with these two resistors. Because current is flowing from this side to this side, so the direction of current here is in this direction, which implies when you're transforming that current source, we are going to first make sure we are having a fixed voltage source. So a fixed voltage source can be determined by determining the effective resistance. Now, let us determine the effective resistance of the 6 ohm resistor and this 6 ohm resistor. How do you determine it? We just use the normal technique of high school of product over sum, because there are only two resistors in parallel. Therefore, 6 times 6 over 6 plus 6 gives us 3 kilo ohm resistance. From V equals IR, we determine now the voltage that will be across the 3 kilo ohm resistor. The voltage across the 3 kilo ohm resistor will be the current which is going through it, which is 2 milliamps, times the resistance it is flowing through, which is 3 kilo ohms, and it gives us 6 volts. Our next step is now to redraw the circuit after transforming the current source into a voltage source, and in this case we can apply any method of determining the conditions needed and its output voltage VOC. It's what we are looking for. So we can use Kirchhoff's voltage law and we take loops. Using the outer loop, we can see clearly that it can give us the current flowing through the entire circuit. The current will not go through the open circuit. You see very well, this is an open circuit, so the current will not go through there. So as the current is flowing from this side to this end, I note the same current that will pass through the 3 kilo ohm. Now, taking this outer loop, it will give us the entire current through the overall circuit, which implies 6I naught plus 3I naught minus 9 plus 6 will give us 0 using KVL. Therefore, simplifying that equation gives us the total current in the circuit I naught as equal to 1 by 3 milliamps. Now, next step is to take an inner loop. Now, let us consider loop 1. Considering loop 1, it gives us negative 9 because the current is flowing through this negative terminal of the voltage source. So negative 9 plus a third by 6, the voltage across the 6 kilo ohm, then plus VOC, which is voltage across the output, the open circuit, voltage across the open circuit of the capacitor. It is giving us 0 using KVL. Okay, this now gives us VOC as 7 volts, which is our initial condition. Now, let us go to the next step. Now, our next step is all about to see what happens when t is greater than 0. We have done all of that sort when t is equal to 0. What happens when t is greater than 0? When t is greater than 0, we are seeing clearly that according to our circuit, as t is greater than 0, the switch opens. When the switch opens, we are having a circuit of a kind that the 9 voltage source is now cut off. It is not taking part in our capacitive circuit. So we are having a capacitor entirely acting as a voltage source or current source. That is the circuit when the switch is opened. Now, opening the switch, you see that the current coming from the 9 voltage source is not going through the capacitor. Therefore, the remaining circuit will be this one. This implies we can use KCL, Kirchhoff's current law, of a node. At that node, you have seen where I'm indicating the arrows coming from and going into, for us to determine the KCL equation. As I said, opening the switch, the capacitor acts as a voltage source or a voltage device, supplying voltage to the entire circuit. Therefore, the current through the capacitor plus the current through a resistor, 6 kilo ohm resistor, plus the algebraics, we are adding the currents algebraically. Therefore, we are subtracting because the current from the current source is going in the negative direction. So minus 2 milliamps, it's giving us 0. Substituting the unknowns for capacitance, we are having the equation below. Now, the next step is to transform that equation into the frequency domain, that is application of Laplace transform. So we are going to transform that equation, the equation with the asterisk, to a frequency domain. S is the complex frequency. Therefore, when we transform the equation into Laplace transform, we get the equation below. Simplifying the equation, we get this equation. Now, when we proceed with simplifying the equation, we have come to a point where we need to apply partial fractions. Therefore, applying partial fractions, as usual, we see that S is in the denominator of K naught constant, so we multiply throughout and we set S to 0. Setting S to 0, we get K naught. Hope you can do it. Try out this yourself. Have a calculator, manipulate it. You come to a constant 12 as K naught. And K1, because it is S plus 66.67, set S to negative 66.67, because you need to take all that to 0. Multiplying through by the same expression in the denominator, we are remaining with K1 as the only constant. And the final expression we are having is of that kind. Now, the next step is to transform the frequency domain equation into time domain equation, which is an easy task, and it's left for you. The final answer is V of t, which is equal to 12 minus 5 exponent negative 66.67 t. Now, as an example, I have done so far 2 examples for you. Let me leave you with another task for you to accomplish. You leave comments in the comment section. Leave questions in the comment section. In the next video to be uploaded, I will answer all your questions about this task. Thank you for watching. Thank you for subscribing. Thank you for sharing the video. Keep watching. Wait for the next session. Have a great time. This is Simon Deo Musoke from Makerere University.